Imagine this. NASA's James Webb Telescope, humanity's most powerful eye in the cosmos, has just been shut down. But why? What could it have possibly uncovered that sent shockwaves through the scientific community, forcing the US to act so quickly? Mercury, the smallest planet in our solar system, seems ordinary at first glance, but beneath its fiery surface lies a trove of secrets that could rewrite everything we thought we knew about space. Diamonds glittering in its terrain, water ice in eternal darkness, and mysterious compounds hinting at life. What is NASA hiding? Stay with us as we uncover the truth. Part 1. James Webb's shocking discoveries on Mercury. For decades, Mercury has been dismissed as a barren, lifeless rock, a planet baked by the sun's relentless heat, forgotten amidst the splendor of its celestial siblings. However, James Webb Telescope has shattered this perception. With its advanced infrared imaging, it has unveiled an astonishing revelation that has left scientists baffled and the public captivated. Mercury's surface isn't just a desolate wasteland, it's shimmering with diamonds. These diamonds, formed under extreme pressures and temperatures, are scattered across Mercury's fiery terrain, glittering like remnants of a celestial treasure trove. This discovery is unprecedented. Until now, we assumed that Mercury's violent geological past, marked by intense volcanic activity and asteroid collisions, left it stripped of anything valuable. But these gems tell a different story. They suggest that Mercury underwent a unique transformation, preserving remnants of its violent origins in a way no other planet has. But the story doesn't stop at diamonds. James Webb has peered into Mercury's darkest recesses, its polar craters. Regions so shrouded in perpetual shadow that even the sun's blazing heat cannot reach them. What it found there defies explanation. Water ice. Let that sink in for a moment. Water, the very element we associate with life, existing in solid form on the hottest planet in our solar system. Even more intriguing, the ice isn't just frozen water, it's laced with organic compounds. These complex molecules are the building blocks of life, akin to the ones that may have sparked life's genesis on Earth. The implications are staggering. Could these compounds have formed through Mercury's unique chemical processes? Or were they delivered by ancient comets or asteroids? And, if life can cling to existence in such an inhospitable environment, what does that say about its potential elsewhere in the universe? Before James Webb, Mercury was considered geologically dormant, a planet long past its prime, devoid of activity or intrigue. But now, this narrative has been turned upside down. Scientists have discovered evidence that Mercury's surface is far from dead. The organic compounds and minerals detected by James Webb suggest that complex chemical reactions are still occurring, driven by the planet's extreme conditions. Imagine the scene. As Mercury's surface blazes under temperatures high enough to melt lead, volatile compounds are vaporized, interacting with solar wind particles. This process may create a thin, transient atmosphere, a so-called exosphere, rich with clues about the planet's past and present. In this chemical dance, Mercury defies its lifeless label, revealing itself as a dynamic, ever-changing world. The discovery of these organic molecules has profound implications for our understanding of planetary evolution. On Earth, organic compounds like these laid the foundation for life billions of years ago. Could Mercury, with its harsh environment and fiery origins, represent a similar starting point for life in some distant, unimaginable form? Or does this discovery hint at something even more extraordinary, an ancient connection between the planets? A shared chemical heritage that binds our solar system together? While scientists are quick to caution against jumping to conclusions, the potential for life, even microbial life, on Mercury is no longer a fringe idea. The organic molecules found in the polar craters are remarkably similar to those found in Earth's most extreme environments. Like the frozen deserts of Antarctica or the scalding depths of hydrothermal vents. These are places where life not only exists but thrives, pushing the boundaries of what we consider possible. What makes these discoveries even more astonishing is the fact that they were made in just a fraction of James Webb's operational lifespan. The telescope was designed to explore the farthest reaches of the universe, to peer into the origins of galaxies and the birth of stars. Yet, in turning its gaze inward, toward the sun's smallest, closest companion, It has unearthed secrets that could redefine our understanding of habitability. Not just on Mercury, but throughout the cosmos. So, what does all this mean? For one, it challenges our long-held assumptions about what makes a planet alive. Mercury, with its searing temperatures and seemingly inhospitable conditions, was once the last place anyone would look for signs of life or complexity. But now, it stands as a testament to the resilience of nature and the infinite diversity of planetary systems. James Webb's findings have only just begun to scratch the surface of what Mercury has to offer. Each new discovery raises more questions than it answers. How did these diamonds form? What ancient forces preserved the water ice in Mercury's shadows? And most tantalizingly, could life, however primitive, exist in a world so seemingly alien? As we venture further into this mystery, one thing is clear. Mercury is not the lifeless rock we once believed it to be. It is a dynamic, enigmatic world, brimming with secrets that may one day unlock the deepest mysteries of life itself. The diamonds, water ice, and organic compounds are just the beginning. The question is, what will James Webb uncover next? Part 2. The giant core and mysterious magnetic field of Mercury. Mercury is often overlooked in the solar system. Yet beneath its cratered surface lies a feature that astonishes scientists, a colossal core. Research reveals that Mercury's core makes up an astounding 85% of its total volume. The largest core-to-volume ratio of any planet in the solar system. In comparison, Earth's core comprises only 15% of its total volume. This massive core raises profound questions about Mercury's formation, evolution, and the forces that shaped it. What could account for such an unusually large core? One prevailing theory is the hit-and-run scenario. In the early days of the solar system, Mercury may have been a much larger planet, but a catastrophic collision with another celestial body likely stripped away much of its outer layers. This violent event left behind an iron-rich core and a mantle only 420 kilometers thick, a mere fraction of Earth's mantle, which is about 2.900 kilometers thick. Such a collision could also explain Mercury's relatively high density and unique composition compared to other rocky planets. However, Mercury's mysteries go far beyond the size of its core. The planet also possesses a magnetic field, a feature that distinguishes it from most other rocky worlds. While Venus and Mars lack global magnetic fields, Mercury's field, though weaker than Earth's, is still significant. What's more perplexing is its asymmetry. Measurements show that Mercury's magnetic field is stronger in its northern hemisphere than in its southern half. An anomaly that has baffled scientists since its discovery. This irregular magnetic field is believed to be tied to the unique properties of Mercury's core. Unlike Earth, where the magnetic field is generated by the flow of molten iron in the outer core, Mercury's field appears to result from a combination of factors. Researchers theorize that Mercury's core consists of a partially molten outer layer surrounding a solid inner core. This unusual structure, combined with the planet's slow rotation and extreme proximity to the Sun, creates a magnetic field that is both weaker and more uneven than Earth's. The Sun itself plays a crucial role in shaping Mercury's magnetic activity. As the closest planet to the Sun, Mercury experiences intense tidal forces that influence the movement of its liquid core. These gravitational interactions generate internal stresses, further contributing to the planet's unique magnetic phenomena. Mercury's elliptical orbit adds another layer of complexity, as the varying distance from the Sun causes fluctuations in these tidal forces, amplifying their effects on the core's dynamics. Mercury's magnetic field also serves a vital function in its environment. Despite being only about 1% as strong as Earth's, it acts as a shield against the relentless solar wind, a stream of charged particles emitted by the Sun. This protective barrier prevents the solar wind from completely stripping away Mercury's tenuous exosphere. Without this magnetic field, the planet's already fragile atmosphere would vanish entirely, leaving Mercury even more exposed to the harsh conditions of space. The existence of a magnetic field on such a small, slow-spinning planet raises profound questions about its history. Could this field hold clues to Mercury's violent past and its early interactions with other celestial bodies? Does the planet's unique core composition suggest processes vastly different from those of Earth and other rocky planets? These questions extend beyond Mercury, offering insights into how magnetic fields are generated on other planets and even stars. Mercury's magnetic field challenges our understanding of what makes a planet dynamic and active. For centuries, it was thought that Mercury, with its small size and proximity to the Sun, would have cooled and solidified billions of years ago, rendering it geologically and magnetically inert. Yet, the presence of a magnetic field, combined with evidence of internal heat and core dynamics, suggests a far more complex reality. Beneath its heavily cratered surface lies a world that defies expectations, its core still spinning and generating forces that shape its environment. Studying Mercury's core and magnetic field provides a unique opportunity to unravel the processes that govern planetary evolution. The discoveries made by MESSENGER have laid the groundwork for further exploration. And the upcoming Bepi-Colombo mission is expected to deliver even more detailed insights. By analyzing Mercury's gravitational field, magnetic field, and surface composition, scientists hope to uncover the forces that drive its internal activity and the interactions that define its relationship with the Sun. Mercury's story is a testament to the dynamic and unpredictable nature of planetary science. Its colossal core and mysterious magnetic field offer a glimpse into the processes that shape not only the smallest planet in our solar system but also rocky worlds across the cosmos. As we continue to study this enigmatic planet, Mercury challenges us to rethink our assumptions about the inner workings of planets and the forces that shape them. Part 3. Ice and the potential for life on Mercury. In a solar system where extremes are the norm, Mercury stands as a paradox. As the closest planet to the Sun, its surface temperatures soar high enough to melt lead. Yet James Webb's recent discoveries have revealed something extraordinary: pockets of water ice preserved in the planet's polar craters. These regions are perpetually shadowed, never seeing a single ray of sunlight, creating oases of icy stillness on an otherwise blazing world. The discovery of water ice on Mercury is a revelation that defies logic. Conventional wisdom would suggest that the Sun's relentless heat would have long since evaporated any trace of water. However, the craters at Mercury's poles are uniquely positioned to remain cold enough, plunging to temperatures as low as -200 degrees Celsius, to preserve this ice indefinitely. These frozen reservoirs are protected by the geometry of the planet itself, as their steep walls cast perpetual shadows that shield the ice from the Sun's scorching rays. But the ice alone is not the most intriguing part of this discovery. Detailed analysis of the ice samples, as captured by James Webb's advanced instruments, has revealed the presence of complex carbon-based compounds. These organic molecules are strikingly similar to those found on Earth, molecules that are closely linked to the origins of life. The presence of such compounds on Mercury raises tantalizing questions. Could these be remnants of ancient chemical processes that once took place on the planet? Or were they delivered by asteroids or comets, which may have seeded Mercury with the building blocks of life billions of years ago? To understand the significance of this, consider Earth's early history. The presence of water and organic molecules in specific environments created the perfect conditions for life to emerge. While Mercury's harsh environment may seem inhospitable by comparison, the discovery of similar components opens the door to extraordinary possibilities. Could primitive life forms, or at least the precursors to life, have once existed in these icy havens? Or could the planet still harbor secrets about life in forms we cannot yet comprehend? Moreover, the implications stretch beyond Mercury. The discovery challenges long-held notions about where life-sustaining conditions might exist in the solar system. If organic compounds and water ice can coexist on a planet as extreme as Mercury, what does this say about the potential for life on other planets or moons with similarly harsh environments, such as Europa or Enceladus? Mercury's icy craters could serve as a blueprint for identifying other celestial bodies that might harbor the ingredients for life. The very existence of these icy reservoirs also tells us something profound about the planet's history. Mercury's proximity to the Sun makes it a prime target for solar radiation, which can break down molecules and strip away water. Yet the ice persists, suggesting that it may be relatively young, perhaps delivered by recent asteroid impacts. This idea aligns with the theory that Mercury has experienced a dynamic history of bombardment. with comets and asteroids serving as cosmic messengers, bringing water and organic materials to its surface. The potential for water ice to persist and coexist with organic molecules also deepens our understanding of how Mercury interacts with its environment. The planet's tenuous exosphere, a thin layer of particles surrounding it, may play a role in replenishing some of these materials, further complicating the narrative of a dead planet. Instead, Mercury emerges as a world in flux, one where even in the most extreme conditions, nature finds ways to preserve its secrets. These findings are not just scientifically groundbreaking, they are philosophically profound. They remind us that life as we know it is not confined to Earth-like conditions. Instead, it may emerge and persist in forms and places we have yet to imagine. Mercury's icy craters, stark and desolate as they may appear, are now a beacon of hope for understanding how life's essential ingredients can arise in the most unlikely corners of the universe. The work of James Webb is far from over. With each new piece of data, we peel back another layer of Mercury's enigmatic story. The ice in its craters, the organic molecules within it, and the conditions that allow both to persist are just the beginning. As we continue to probe deeper, the planet challenges us to rethink what we know about habitability, resilience, and the boundless possibilities of life in the cosmos. Part 4. Volcanic activity and the mysterious geological history of Mercury. Mercury has long been dismissed as a geologically dead planet, a lifeless world where the sun's scorching heat has rendered it barren and static. However, recent findings from the MESSENGER mission and the James Webb Telescope tell a very different story. Evidence of ancient volcanic activity and other unique geological features reveals that Mercury's surface was once alive with dynamic processes. And it may still harbor some degree of geological activity today. The northern volcanic plains on Mercury are among the most striking indicators of its fiery past. These expansive flatlands, formed billions of years ago, are believed to have resulted from massive lava flows that erupted from Mercury's interior. These eruptions likely covered older craters and reshaped vast portions of the planet's surface, leaving behind the smooth, featureless regions observed today. The scale of this volcanic activity rivals that of Earth and Venus, suggesting that Mercury was once a geologically vibrant world. But volcanic plains are not the only clue. Mercury's surface also features unique formations known as hollows. These shallow, irregular depressions are unlike anything found on other planets. Scientists believe they are created when volatile compounds near the surface are vaporized by the sun's intense heat. As these materials evaporate, they leave behind these enigmatic features, which are scattered across Mercury's terrain. The existence of hollows suggests that even today, the planet is not entirely dormant. Instead, it is slowly evolving under the relentless pressure of its harsh environment. Adding another layer of intrigue, data from the James Webb Telescope has confirmed the existence of an ancient magma ocean beneath Mercury's surface. During the planet's early history, this reservoir of molten rock would have been a seething cauldron of activity, shaping the planet's internal structure and surface features. As the magma gradually cooled and solidified, it likely contributed to the formation of Mercury's massive core, which now accounts for an astonishing 85% of the planet's total volume. This is the highest core-to-volume ratio in the solar system and one of Mercury's most perplexing characteristics. The discovery of this ancient magma ocean is a game-changer. It suggests that Mercury underwent a process of differentiation, where heavier elements like iron sank to its core while lighter materials rose to the surface. This process, driven by the intense heat of the planet's formation, would have fueled extensive volcanic activity and reshaped its surface multiple times. The volatile compounds that contributed to the formation of hollows are likely remnants of this violent history, preserved on Mercury's surface for billions of years. Recent analysis has also suggested that Mercury's volcanic activity may not be entirely a thing of the past. While large-scale eruptions ceased billions of years ago, smaller-scale geological activity may have persisted into more recent times. Chemical signatures detected on the surface indicate that volcanic processes could still be influencing the planet's composition, albeit on a much smaller scale. This discovery challenges the notion that small, rocky planets like Mercury lose their internal heat quickly and become geologically inert. Volatile materials such as sulfur, potassium, and sodium detected on Mercury provide further evidence of its dynamic history. These elements, which would typically be driven away by the sun's heat, are believed to have originated deep within the planet and were brought to the surface through volcanic activity. Their presence on Mercury is surprising and suggests that the planet's geological processes have played a crucial role in preserving these materials over time. The Sun itself may have played a role in Mercury's geological evolution. Tidal forces exerted by the Sun, combined with the planet's eccentric orbit, may have triggered massive quakes and eruptions throughout its history. These interactions between Mercury's internal processes and its external environment add a fascinating layer of complexity to the planet's story. Mercury's volcanic history is not just a testament to its resilience but also a window into the broader processes that shape rocky planets. The discovery of ancient magma oceans, mysterious hollows, and volatile compounds has transformed our understanding of the smallest planet in the solar system. Far from being a static relic of the past, Mercury emerges as a dynamic world that has defied the odds to retain some degree of geological activity. As we prepare for the arrival of the BepiColombo mission in 2025, there is every reason to believe that Mercury still holds many secrets. Each new discovery brings us closer to understanding not only Mercury's geological past but also the forces that shape planets across the universe. Mercury may be small, but its story is immense, a testament to the dynamic and ever-changing nature of our solar system. Part 5. The Sun's influence and Mercury's strange orbit. Mercury's relationship with the Sun is nothing short of extraordinary. As the closest planet to our star, it experiences phenomena unlike any other world in the solar system. Among these, its peculiar orbit and day-night cycles stand out as some of the most fascinating and puzzling features. Mercury's day is significantly longer than its year, while it takes just 88 Earth days to complete one orbit around the Sun. A single day on Mercury, defined as the time it takes to rotate once on its axis, lasts a staggering 176 Earth days. This unusual spin-orbit resonance, where Mercury rotates exactly 3 times for every 2 orbits around the Sun, is a result of the Sun's immense gravitational influence. Over billions of years, tidal forces from the Sun slowed Mercury's rotation, locking it into this unique pattern. This peculiar resonance creates a surreal experience on Mercury's surface. As the planet moves through its orbit, the Sun appears to perform a bizarre dance in the sky. In some regions, the Sun seems to pause, move backward briefly, and then resume its forward motion. This effect, caused by the interplay of Mercury's slow rotation and fast orbital motion, makes the planet's day-night cycle one of the most complex in the solar system. But Mercury's strange orbit is not just a celestial curiosity, it has profound effects on the planet's internal structure. The Sun's tidal forces generate significant stress within Mercury's crust and mantle, causing them to flex as the planet moves closer to and farther from the Sun during its elliptical orbit. This constant flexing generates heat through friction, a process known as tidal heating. Although Mercury lacks the intense geological activity seen on moons like Io, this mechanism may still contribute to maintaining some internal heat. This heat plays a critical role in Mercury's geology. Despite being much smaller than Earth and losing much of its original heat billions of years ago, Mercury's core remains partially molten. Scientists believe that tidal heating, combined with the planet's unique orbital dynamics, helps sustain this molten state, enabling the generation of its weak but persistent magnetic field. Without this interaction with the Sun, Mercury's core might have solidified entirely, leaving the planet geologically dead. The Sun's influence extends beyond the planet's interior. Mercury's proximity to the Sun exposes it to an intense solar wind, a stream of charged particles that continually bombards its surface. This interaction contributes to the erosion of Mercury's already tenuous exosphere, a thin layer of particles that surrounds the planet. At the same time, the solar wind may also replenish some of the volatiles on Mercury's surface, creating a delicate balance between loss and gain. Mercury's orbit and its close relationship with the Sun provide a unique laboratory for understanding tidal forces and their effects on planetary bodies. By studying these interactions, scientists can gain insights into similar processes that may occur on exoplanets orbiting close to their stars. These findings could help us better understand how planetary systems evolve and how conditions for habitability might emerge under extreme circumstances. As we continue to explore Mercury, its orbit and interaction with the Sun remind us that even the smallest planets can exhibit some of the most complex and fascinating dynamics. Mercury's story is a testament to the intricate and often unexpected ways in which celestial bodies are shaped by the forces of the universe. Part 6. Hidden Secrets Beneath Mercury's Surface. Mercury's surface, with its craters and ridges, offers a glimpse into its tumultuous past, but the real mysteries may lie beneath its rocky crust. Recent studies, fueled by data from the MESSENGER mission and ongoing analysis, suggest that Mercury's interior is far more dynamic than previously believed, with the potential for geological activity still persisting deep below. One of the most intriguing discoveries is the presence of extensive fractures and fissures within Mercury's crust. These cracks, formed over billions of years due to the planet's cooling and contraction, are more than just scars of geological history. They may serve as conduits for heat and, potentially, liquids to move between the planet's layers. This movement could explain some of the planet's surface features, including the mysterious hollows and the distribution of volatile compounds like sulfur and potassium. The idea of subsurface activity on Mercury is revolutionary. For decades, scientists assumed that small, rocky planets like Mercury would lose their internal heat quickly, becoming geologically inactive. However, evidence now suggests that Mercury's interior still retains enough heat to sustain limited activity. This heat, generated by the slow cooling of the planet's massive core and potentially enhanced by tidal forces from the Sun, could drive interactions between the crust and the mantle, creating localized geological phenomena. One of the most tantalizing prospects is the potential existence of subsurface water reservoirs. While Mercury's surface is arid and inhospitable, data indicates that pockets of water may be hidden deep below the crust. These reservoirs could represent remnants from an earlier time when Mercury was more geologically active. Or they may be sustained by internal heat preventing the water from freezing completely. Similar phenomena have been observed on moons like Europa and Enceladus, where subsurface oceans exist beneath thick ice sheets. The implications of such a discovery are profound. Subsurface water, even in small quantities, would reshape our understanding of Mercury's history and its potential for habitability. While the planet's harsh surface conditions seem incompatible with life as we know it, the presence of water below could provide clues about the chemical reactions that may have occurred over billions of years. These processes could resemble those that led to the emergence of life on Earth. Furthermore, the presence of water deep within Mercury's crust could explain the volatile compounds detected on its surface. As the planet's interior cools and contracts, pressure from below could force these materials upward through cracks and fissures, depositing them on the surface. This process might account for the surprising abundance of volatiles like potassium and sulfur, which would otherwise be expected to dissipate in Mercury's proximity to the Sun. Exploring these subsurface mysteries presents significant challenges. Mercury's extreme temperatures, combined with its thin exosphere and close proximity to the Sun, make direct exploration difficult. However, upcoming missions like BepiColombo, with its advanced suite of instruments, are poised to shed light on these hidden processes. By studying the planet's gravitational field, magnetic field, and surface composition, scientists hope to uncover more about Mercury's interior and the forces that shape it. The possibility of active processes beneath Mercury's surface challenges our perception of what a dead planet looks like. Even on a small, sun-scorched world like Mercury, there may be pockets of activity that continue to shape its evolution. These findings remind us that planetary science is full of surprises, and the smallest planets can hold the biggest secrets. As we await further insights, one thing is clear: Mercury's story is far from over. Beneath its rocky surface lies a world of possibilities, waiting to be uncovered by future exploration. The secrets hidden within Mercury's crust could unlock not only its past but also the broader mysteries of planetary evolution across the solar system. From dazzling diamonds and polar ice to mysterious geological activity, Mercury is far more than a small, scorched planet. It's a scientific treasure trove awaiting discovery. But why would NASA hide these groundbreaking revelations? Could it be that we're inching too close to truths they're not ready to reveal? Stay tuned to uncover more secrets about this enigmatic planet. If you love unraveling cosmic mysteries, like, share, and subscribe to our channel. Thank you for watching.